So what is a factor? A factor is an integer number that divides exactly into another number. So definitions in math are tough. Examples are usually a quicker way to see it. An example is 3 is a factor of 15 because I can divide 15 by 3 and I won't get a remainder or a decimal. And because 3 times 5 is 15, that means 3 and 5 are both factors of 15. A factor of 12, well, 2 divides into 12, 6 divides into 12, 3 and 4. So those are what factors are. A prime number is a number that we can only divide by 1 in itself. So another way of saying that is it only has 2 factors, 1 in itself. Examples, well, a number that I can only divide by 1 in itself might be 7. Can't divide 7 by anything else, only 1 and 7. There's actually an infinite number of primes. They get further and further apart. 3 is one, but I think I was going to write down 31. Can't divide 31 by anything except for 31 and itself. Anyway, yeah, there's infinite primes, and there actually are thousands of computers all around the world looking for the next prime. There's no formula to find the next prime, so it takes a lot of computing power, and primes now are millions of digits long to find the next prime, because they go on forever, and it's kind of an interesting math problem to keep finding bigger and bigger ones. We're not going to deal with prime numbers that are that gigantic, but you can kind of think about any number that I can't divide it. I can only divide it by itself and 1, which, of course, every number we can divide by. When I say factorizing a number, that means I'm going to write the number as a product of other natural numbers. What are natural numbers? Those are just positive numbers that we can count on our fingers. 1, 2, 3, 4. Those are natural numbers. 3.8 isn't a natural number. -7 isn't a natural number. So to factorize means that I'm just going to write 24 as a product of 2 numbers. 3 times 8. So I factorized it by writing it as a product of other numbers, by writing the product of its factors. There's obviously different ways to factorize numbers. 12 times 2 also works. To factorize fully means I'm going to write it as only a product of primes. So for example, 36, if I was going to write it as a product of primes, well, I could start by factoring it into 4 times 9, but 4 and 9 aren't primes. So I'm going to break down each of those. 4 is 2 times 2, and 9 is 3 times 3. Now I've factorized 36 fully because all 4 of these factors are primes, right? 2 and 3 I can only divide by itself. We're going to do a couple examples. Again, you might want to pause the video and work on these on your own. Factorize 36 in 2 different ways. So I could write 36 equals 12 times 3. That's one way to factor. Or 36 equals 6 times 6. So again, I'm just breaking it down to the product of 2 natural numbers. Some wise guy, if we were in class, would always say 1 times 36. That also works, right? So 2 numbers that multiply to 36. 95, same thing. I could break that down into 5 times 19. And this is a little bit easier if you know your times tables, but we should know that 95 divided by 5 because it ends in a 5. And I think I might have to do this 1 times 95 option. So any number that isn't prime, I can factorize in multiple ways. If a number is prime, I can only do that 1 times itself version. In our next example, we're going to factorize fully. And what this means is that I'm going to break this down into prime numbers. We're going to do this with a factor tree. You may have done this in elementary school. You may not have. So we're going to start by breaking down 27 into 2 factors. Let's say 3 and 9. And I'm going to keep going until I only have prime numbers at the end of my branches. So 3 is already prime. I can stop. 9 is not prime. And now each branch ends with a prime number. So we can factorize 27 fully by saying it's 3 times 3 times 3. And to save space, or to write this in kind of a more organized notation, I can say that's 3 to the power of 3. That's a fully factorized version of 27. Again, there's lots of ways to start. So I'm going to start by breaking down a number. I know I can divide 72 by 6. I'm going to do 12 times 6. You could start this with 9 and 8. We're going to get to the same place. I want to break each of these down until I only have primes. 6 I can break down into 3 and 2. 12 I can break down into, let's say, again, I've got a few ways sorry, that I can factorize. 12, I can break it down into 3 and 4. 4 still isn't prime, so I can break that down into 2 and 2. So the fully factorized version of 72, well, I've got 3 2's. So I can write 2 to the power of 3, which is 2 times 2 times 2. I've got 1, 2, 3 2's. And I've got 2 3's. So I can do 2 to the 3 times 3 squared, or 3 to the power of 2. So again, I'm breaking down 72 and rewriting it as a product of only prime numbers. The last one, 90, okay, well, it ends in a 0, so I can definitely divide it by 10. 9's not prime. We've done this a few times. I can break 9 into 3 and 3. Those are both primes. Can I factorize 10? Yes, 2 times 5, though they're both primes. So 90 equals 2. There's 1 2 at the end of a branch. I've got 2 3's, so I can write 3 squared, and then 5. It's usually convention to write this from the smallest prime factor to the largest, but that's an example of factorizing fully. So factoring means to take a number and to write it as a product. What we're going to move on to today, which again should be reviewed from grade 9 math, is what's called common factoring. And this is the opposite of the distributive property. So when we do the distributive property, which means I'm multiplying what's in front of the bracket by everything inside of it, x squared plus 2x. I'm writing this multiplication question. This is a multiplication question, x times x plus 2, as an addition question. I'm going to do the opposite. I'm going to take this addition question and rewrite it as a product. So it's really about dividing. And what I'm asking myself is, what can I divide both of these terms by, or what do these terms share? In this case, x squared and 2x both share an x. So I can divide both these terms by x and move that out front. When I do the division, x squared divided by x, well, that's just x. And positive 2x divided by x, which is positive 2. My x's are going to cancel out. So if we compare the left and the right, common factoring is just kind of going backwards or doing the opposite of the distributive property. And we're going to go through a few methods to common factor today. When we're common factoring, the first thing I'm going to do is I'm going to treat the coefficients, which is the number in front of the variable, kind of on its own, and then I'm going to treat each variable separately. So I'm going to look for the biggest common factor of the coefficients, what number divides into both. Then I'm going to look for the large factor of each variable. So that's another way of saying how many x's will go into each term. And then whatever remains, that's my greatest common factor. So in this first example, I've got two terms. I have 8x squared and 12x to the 5. Well, what do 8 and 12 share? What's the biggest number that divides into both? So that's going to be 4. How many x's can divide into x squared and x to the 5th? So what I'm trying to do is, how many x's do they share? Well, they share 2. This one only has 2 x's. This one really has 5. If it helps, you can kind of think about that. X squared equals x times x. X to the 5th equals x times x times x times x times x. So they each share 2 x's. So my greatest common factor is going to be x squared. So 4x squared is shared by both 8x squared and 12x to the 5th. That's my greatest common factor. Here I've got two, these are still just terms, right? They're not separated by a plus or a minus sign. I'm going to look at first the coefficient. What do 14 and 21 share? Well, they both are divisible by 7. X cubed and x squared, well, those share 2 x's. So it's essentially the smallest number that they share, the smallest number of x's. Y to the 6 and y squared, again, those share 2 y's. And then z to the 7 and z to the 3, those each have at least 3 z's. So my common factor is 7x squared y squared z cubed. I hope I didn't say z, I want to say z, as we're Canadians here. Okay, so that's how I find the greatest common factor. We're going to use that now to fully factor these expressions. And there's kind of two steps. The first step is to find that greatest common factor. So in example A, I've got 2xy plus 14y. What do those share? Well, 2 and 14 are both divisible by 2. Okay, they don't share an x. This is 0 x's, and that is 1. But they do share a y, so 2y is going to be my common factor. So then what I'm going to do is I'm going to divide both terms by 2y and write the results of my division. What's 2xy divided by 2y? Well, the 2's cancel out, the y's cancel out, I'm left with just x. What's 14y divided by 2y? Well, the y's cancel out, and then 14 divided by 2 is 7. So this is now the fully factored version. I know it's fully factored because what's left in the brackets, these shouldn't share any common factor, and they don't, x and 7. What's nice about common factoring is I can always check my answer just by distributing. So I'll do that in red here. So I can do the opposite. I can do 2y times x plus 7. And maybe we're more used to this, so that's going to give me 2xy. When I multiply these together, when I multiply 2y by 7, I get a plus 14y. And I'm back to where I started. So again, factoring is the opposite of expanding and simplifying. Okay. In my next example, I've got 3 terms. There are 3 separate products separated by addition and subtraction signs. What do they share? 7, 21, and 14. Well, I can divide those all by 7. They share 7. X squared, x, and no x's. So they're not going to share any x's, but they are going to share y, y, y. So 7y is shared by each of these 3 terms. We're kind of looking at what's the biggest thing they share. And my second step is, again, to divide each of these terms by 7y and write the results in my brackets. So I'm going to have 3 terms. The first one's going to be what's 7x squared divided by 7y? Well, the 7's cancel out, the y's cancel out, and I'm left with just x squared. 21 divided by 7 is 3. The y's cancel out, so I'm left with 3x. And then 14y divided by 7y, the y's cancel out, and I'm left with it too. So I still have the same number of terms, but I'm now expressing this addition statement as a product, which is what we call fully factored. So my GCF is out front, and then whatever left from my division, which is called my quotient, is in the brackets. And again, I could check if I wanted to by distributing, which I'm not going to do in this example. Okay, here I've got 2 terms. What do they share? Well, 8 and 4 both share a 4. X cubed and x8, well, they both share a minimum of 3 x's. And y to the power of 7 and y squared both share at least 2 y's. So again, we're kind of treating the coefficient first, and then we're looking at each variable separately. Once I find the greatest common factor, the next step is to divide by that common factor. Eight x cubed y to the 7 divided by 4x cubed y squared. Well, 8 divided by 4 is 2. X cubed and x cubed, if it's the same on top and bottom, they cancel out. Y7 divided by y squared is actually y to the 5th. And you may remember that from your kind of grade 9 exponent rules. I'll show you on the right what's happening there. Y to the 7 divided by y squared. Well, what that really is saying is I've got 7 y's. I'm going to write out 7 y's divided by 2 y's. And so when I cancel y, I'm left with just 5 y's multiplied together still, so I'm left with y to the 5. The exponent rule for that is when I'm dividing exponents with the same base, they're both y, I'm just subtracting the powers. So y to the 7 divided by y squared equals y to the 7 minus 2, which equals y to the 5. I know that green pen hopefully comes through in the video. So I'm left with 2y to the 5, and I'm going to do my division again. This time the 4's cancel out, the y's cancel out, and x to the 8 divided by x cubed is going to be x to the 8 minus 3, or x. And again, I can check my answer by distributing, and my 2 terms, or any number of terms inside the brackets, should not share any common factor. So let's keep going. What do the coefficients share? 12, 24, and 36. Well, they all share 12. I can divide each of those coefficients by 12. X to the 5, x to the 3, x squared all share at least 2 x's. So then I'm going to divide each of these terms by 12x squared. And if you don't need to write the 12x squared on the bottom, that's fine. You're going to do the division in your head as we practice. 12 divided by 12 cancel out. X to the 5th divided by x squared. I'm left with x cubed. 24x cubed divided by 12x squared. Well, 24 divided by 12 is 2. X to the 3 divided by x to the 2. I'm just left with 1x. 3 minus 2 is 1. I don't need to write the 1. Minus 36x squared divided by 12x squared. I'm going to be left with just a 3 because my x squareds are canceling out. And again, I could check by distributing. We'll just do one last one. What do 42, 2, and 6 share? They only share that 2. I have A, and A in all 3. I have at least one C, but only one C. And they don't share the D's because my last one is 0 D, so it can't be part of my common factor. I'm going to divide each of these by 2AC. I'm going to have 21 CD plus D minus 3C. So again, I didn't necessarily write all the division down. So you can check with your answer to see if you agree with what I've done. And again, we can also check by distributing. Once I distribute the term in front, I should end up back where I started. So that's common factoring. What I'm really doing is dividing or moving out front the largest common factor shared by all of the terms in an expression. Again, there's factor problems in the textbook. Give those a try. Email me with any questions, log into Study Hall, and then there'll be a Brightspace check-in. It's all multiple choice, should only take you around 20 to 30 minutes, and you're gonna practice multiplying binomials and also greatest common factoring. Okay, best of luck with that, and please don't hesitate to reach out with any questions. Okay, have a good day.